Okay, so I think we'll go ahead and start. I think there may be some more joining as we go, but we'll get started. So we have a webinar today sponsored by the OPC Foundation. It's on oil and gas platforms and the OPC UA interface that we use on them. We have as part of the webinar, you can ask questions. All of you are muted, but there's a question dialogue in the webinar. So please feel free to type questions in. We'll answer them at the end of the session when we have a question and answer session. So remember, ask questions and we'll make sure we get to all of the questions when we're done. So let's begin. First thing we have is a little bit of introduction. So I'm Paul Hunker. I'm a OPC UA expert. I run my own consulting company and I spend much of my time dealing with OPC UA. I'm an editor for parts of the OPC UA base standard. I'm also one of the leaders and or editors for the MDIS companion standard, which we'll talk about more and provide a little more information about. So I'll let each of the other presenters introduce themselves briefly. So Andrew.
Yeah, my name is Andrew Capello, and I work for FMC Technologies. My specific role is in a division called UCOS Products Group out of California, and I'm the UCOS Product Architect. And I oversaw the implementation and ongoing implementation of an MDIS compliant server. It's a generic OPC UA server capable of supporting all the functions necessary for MDIS, and we'll get into a little bit more during my presentation.
Vijay.
Hello, I'm Vijay and I work for Yokogawa. I'm a systems architect here and I'm looking at the MDIS specifications, bringing them into Yokogawa products.
Okay. Thank you, Vijay and Andrew. Both of them will have more to say later on in our presentation. So let's go on a little bit. What is MDIS? Well, let's start a little bit with what we're talking about. We have oil and gas platforms. We see the picture there on the right. They have topside controls, subsea controls, and the control systems on these platforms are provided by multiple vendors typically. So on these platforms, there's sort of an integration nightmare, right? So most of the systems, there's a distributed control system, a DCS on the platform, and then there's also subsea controls. So a subsea control system or a gateway to the subsea equipment. Currently, communications OPC-DA or Modbus. Typically, there's a few other protocols that can be used too, but the key thing is that there's a suite of protocols available, and most vendors implement different choices. And some of the protocols, Modbus in particular, is a bit on the older side. So there's a lot of work on integrating these systems in. There's documentation on how the interface should work. There's an exchange of information that happens. There's the protocols itself. They vary. They have different capabilities. Modbus is just an RS-232. It has bandwidth issues. The data that comes across is bits and bytes in some of the protocol. So it's hard to map it and generate data from it. So, every project is very custom and specific. There's a huge amount of testing work that is required on these systems because you have to verify all the points and make sure everything works appropriately. And most of this testing information or testing can't be done until very late in the development cycle of a project. So that has its own headaches and drawbacks. If you encounter a problem that late in the project, it's very expensive to fix because you have to re-engineer a whole bunch of things. So what happened is the operating companies, so these are the big name oil companies, got together and realized that we need a standard. We want a standard way of providing this communication, and the information we want to communicate, we want it to be standard. So, the communications between the subsea gateways, the MCS systems, which is the control systems for the subsea equipment, and the DCS, which is the platform-specific controls, want to have a standard communications architecture. So this is where MDIS, the MCS DCS Interface Standardization Organization, was formed. And it was through the action of a number of operating companies. So what is it? It's basically formed by all the major operating companies. So pretty much every major oil company's had a hand in it or is currently active in it. All the major DCS vendors are involved, and almost all the subsea vendors, although my background is more on the DCS side, so I don't necessarily know all the subsea vendors, but I've been told that pretty much all of them are involved. Um, the key thing is the operating companies agreed to require the MDIS information model once it's been released. And the big goal here for MDIS is to reduce engineering and testing and the costs associated with both, so that these multi-year platform operations can be done a little quicker and also at a much lower cost. So what's the scope of MDIS? They've decided on a communications protocol. They want to set up a object model for what's being exchanged. So where are we? They've chosen OPC UA as the communications protocol. It's the way that the subsea system and the gateways and the MCS or the DCS systems are all supposed to communicate. They've defined architectures for the systems. They want to have models for the major devices, and those are available. Oh, but they don't want a standard that's just a paper standard. They want to make sure there's validation and testing. And then they've also realized that you can't specify everything in a standard and make everybody behave the same. Heck, vendors have different products and different abilities in their products. So they want to further it by providing a recommended practice document that describes how the varying variances should be handled and addressed so that the systems can work fairly seamlessly and easily. So where are we? The MDIS body has multiple active subgroups in it. And two of the groups, the architecture group is pretty much done. They've released a spec a number of years ago already that defines the architectures they expect to see in the systems. Objects group is currently working on objects, but they're pretty much complete too. So they've been suspended and say they're done. There's two active groups working at this point still, and they're the validation group that describes how to standardize tests and what tests should be done, and then a recommended practice groups, which describes the multiple options and how they should be handled. MDIS has meetings 4 times a year. They have weekly conference calls. So part of it is that if you're interested, you could always join the MDIS groups too. Let's talk a little bit about the architectures. So in a MDIS system, there's the DCS system, and it talks to the subsea vendor systems. And when you look at these systems, there's a flow of information in object models. But because there's some variances in the architectures, in particular, some operating companies choose to have one vendor that provides all of the controls. So in that case, they provide the DCS controls and the MCS controls, and they only communicate with the subsea vendor's equipment through a gateway, and that's where the MDIS interface will reside. In the alternate architecture, there's a DCS vendor that provides the platform controls and displays. Then the subsea vendor provides the control equipment and the controls for the subsea equipment, and they communicate through their own gateway. The difference here is in the amount of information that needs to flow between the systems. If you need to have all of the controls in the DCS, then more information has to come up through the subsea. And if the MCS has the information or the subsea system has the MCS controls, then there can be less information flowing up to the DCS system because some of it is handled just by the subsea system. It's a choice, vendor-specific choice, or more particular, an operator-specific choice as to where they configure it. And thus there's two models, but the models actually affect the actual object models too. So the key thing here is that the reason that the object models vary is because some of the controls may be up in the subsea system or maybe down. Here's an example of some of the shutdown signals or hydraulic power unit information as to which system it reports to. So it affects the amount of data that's transferred between the two. Both options are used. Sometimes there may even be a mix of the two, depending on the data. So let's talk a little bit about the object models that MDIS has defined. So they've defined a valve and a choke and some instrument and discrete and digital type data. This sort of gives you close to 80% of what's in a well. There's a whole lot of other equipment that they've identified, maybe 20 or 30 additional pieces. And these pieces of equipment vary a great deal from vendor to vendor. So it's much harder for a standard information model to be defined for those pieces of equipment because each subsea vendor may make a different form of that piece of equipment. They have the same functionality, but they have different, extensions or abilities, and they can provide additional or different pieces of information. So in the OPC UA information model, we realized we needed to make a hierarchical sort of model. So there's sort of a base object type that provides some information, and then there's subtypes of that provide information specific to the models we've created, so digital or discrete or an instrument or chokes or valves. And then some of those models are further extended to provide an output value sort of version or a discrete version. So, one of the key features of OPC UA is that it allows you to easily subtype or extend information models. And client systems can understand the extensions, or they can just deal with the system as if it's the base type. So this allows for easier integration. So, a base type in the MDIS model generates just some fault and warning information and some configuration information to allow a client vendor or a client display system to understand where the source of this point is. And then it has enabling or disabling of equipment capabilities. And then when you subtype it to create such as a discrete instrument, it just adds additional state information. Or if it's an output, then it may add a method that allows you to write information. We'll talk about those a little bit more yet too, in particular with this valve object. In a valve, there's a lot more additional information that's there. There's information about whether this valve's okay to be operated, so interlock information. And this information may vary from valve to valve, not just valve types, but actual instances of valves. So we made sure we modeled the capability that interlocks are available on a instance basis. And in the older systems, in particular in the classic OPC or in a Modbus interface, when you wanted to make a valve move, you had to first set a number of values, double check that all those values are set to the right thing, and then issue tell the valve to move. And that was painful and problematic even because if someone changed one of those settings, the valve may not do what's expected. In the OPC UA model, we added methods. So method allows me to make a single call that passes all of the parameters and all of the data that I expect the system to have as a single call. So it eliminates all that handshaking and checking that was required. I could just make a call and get the information across to the system. So it's one of the things we've added in MDIS object in a valve. Now note, I said that we had about 80% of a well covered here. There's other types that you need, but as part of the recommended practice, which we'll get into a little bit more too, we've created ways to aggregate or create those additional objects on a project by project basis. So part of the additional information we put into the object model specification is we actually had interactions of the models. So we want to be able to show how an object model such as a valve here is supposed to behave when it gets a move. So we want to make sure that the behavior of these different pieces of equipment from multiple vendors matches up well enough that the DCS system that's the client in this system can understand and always expect the same behaviors. So, in this case, when you issue a move command, you first have to check that the valve is actually allowed to move. It's enabled. It doesn't have an interlock present. Then the command would be accepted and the valve starts moving, but valves in subsea systems take a little while to move, so it's moving for some point of time. At some point, it'll change and report back that the valve successfully completed its move. In subsea systems, there's data about the move that's recorded, and it's a way for the operator to determine if the valve actually fully opened. So they're called signatures. And this data takes a little while to collect. So at some point in time, the subsea system would also report back that the valve signature is ready and available, so that the operator can confirm that the valve is actually moved. So these are all pieces of information that we've built into the information model, the OPC UA information model that's available with the system. So we talked about the fact that not everything is always exactly the same. So there's the two architectures. There's the integrated and the interfaced architectures. These make some variances on the models. And there's a recommended practice document that's being generated. It's a separate document from the OPC UA MDIS companion standard, but it provides guidance and recommendations for things that are going to be project specific and may vary between projects, such as which architecture you've chosen, or maybe security settings or performance requirements, redundancy, how you expect redundancy. Platforms always have redundant systems. It's very important. But each vendor has a different way, perchance, that they will be implementing the redundancy. Data priority is another feature. The other things that you can have is object aggregation and extension. So how do objects get aggregated or extended? How do you build the custom types and vendor-specific types? So these are all things that are described in a recommended practice document. Another key feature from the OPC UA or from the MDIS point of view is that they want these models to be validated, and they want to eliminate a lot of the testing headaches. So there's third-party testing that they want to have on the interfaces so that we can be sure that a system is running correctly long before they're ever plugged together and deployed. We want to make sure that there's conformance to the UA standard, but also conformance to the MDIS specification and models. So the validation group is working on all of this to make sure that there's fairly strict adherence to the information models. Lastly, what the validation group also works on is interoperability events. So these interoperability events are events where we bring together all the vendors and clients, both the server and client vendors, and let them check and test their systems. So back in June of this year, we had a interoperability session in Amsterdam where people brought real hardware and software, sometimes emulations. They tested all the OPC UA key features, made sure they were working right. We tried subscriptions and robust communications. But the main thing we did is validate the object models and information models. And we made sure that clients and servers can interact and get their data. So we had 7 clients, 7 servers from almost, I think one vendor brought both a client and a server. So we had 13 different vendors bringing things to the show, and it was nice interactions. We had a series of operators there observing it, and some of the key things here is that as part of the IOP, you had to switch between clients and servers. So a client had to switch to talking to a different server. They did this in a matter of minutes. It didn't take hours to re-engineer or change. Systems just switched quickly. So we have another IOP scheduled for September of next year. This is in Houston. This IOP will have all the final models in it. It'll have robust communications. We're going to have people bring redundancy. We're going to have real hardware and software from vendors. We're going to have information modeling capabilities visited too. So part of the full field layout that we've spec'd includes a bunch of equipment that is not in the list of those 80% of a well equipment. So we're going to expect people to make use of the aggregating and extension options to generate the additional pieces of equipment that they need for a whole field. And then the other big thing about this is it's going to be open for observers, so other people can come watch and see and learn about what the MDIS is. And shortly after this IOP, we plan on formally releasing the specification. It'll be a release candidate much before that. Actually, probably sometime in the next few months, it'll go to a release candidate. But the idea is that we want to validate all of the hardware and validate all the systems before we actually fully release the spec to make sure that no one has a gotcha or we find something afterwards that doesn't work right. So this is a test, and then we'll have a actual released OPC UA MDIS companion specification. So with that, I think we're going to pass it on to Andrew, and he'll spend a little time talking about a subsea system.
Yes.
So Andrew, you should be presenter now.
Yeah.
All right.
Okay. All right. Yeah. My name again is Andrew Capello from FMC Technologies, and my primary role is as the product architect for a software product within FMC called UCOS. And UCOS is first of all, UCOS stands for User Configurable Open System, and it's a platform-independent, IO-agnostic, object-oriented control system. And we use the fundamental technology in UCOS to extend the MDIS interface to our subsea system. And the intention was to do it in a way that would not only allow us to extend it for the MDIS purposes, but also be able to be used in either the interfaced or integrated solution. Also to be used in conjunction with other data models, not just MDIS. And also to be used to extend existing data models or customize UA objects. So first I'll discuss a little bit about how we did that and the underlying technology, and then I'll give a quick demonstration of a server configuration. So first a little bit about UCOS. The atomic unit of control in UCOS is something we call a template, and these templates express control algorithms and presentation information. So a template in our system contains tag definitions, logic, and graphical display information. And UCOS users can create their own templates with editors that we provide in the product, or they can use templates that were created by UCOS product group for specific purposes. And using these templates, a user can quickly and easily put together control solutions. So again, these object-oriented UCOS templates are created to represent real-world devices or internal devices. In other words, you might create a template to represent a real-world valve, or you might create one to represent also a kind of something more virtual, like a shutdown sequence. In this case, for MDIS, we created templates that represent overlays on real-world devices in our system. UCOS internal templates can be used, again, to model connections to external subsystems and other sort of high-level process control algorithms. So once templates have been selected or created, the next phase begins, which is creating instances of the templates. And we call those instances devices. Usually there's one device created for each real-world device. And there's in the next step we will put the graphical instances of those devices onto HMI screens. Now, in this context, we just did it for the purpose of being able to see what the internal status of the MDIS object was. So, for example, in the interop, we wanted to be able to get feedback when a DCS sent a valve command, for example. And then after the HMI is configured, you can set up any real-world I/O. In this case, that would be I/O to our subsea system, which is our 722 protocol. and I'll get into that a little bit more later. But once the process is complete, the configuration is distributed to operator workstations and our field control unit, our controller, which actually executes the UA interface along with the logic. So you go from a template, which has got tags, logic, and graphics, create your device instances from that template. And you distribute those device instances out to an HMI station or the field control unit. So here's a little bit about our thinking behind going to OPC UA and what we hope to achieve. Obviously, there's the lack of future support for COM and DCOM. And another thing that was very attractive was the platform-independent support for UA. We run on a number of different operating systems and have that requirement. So the having to run on Windows for the old OPC model was difficult. And the other things that we found very unique was that OPC UA is inherently object-oriented, just like the underlying system, our underlying technology. And because UCOS is based on these principles, it's ideally suited to support an OPC UA interface. So we provided a user or a UA interface and server configuration application that leverages the template concept. So the UA interface provides an editor that allows you to create your own custom definitions or extend existing ones, and you can also import models, as we'll show here. And UA objects can consist of a number of variables to exchange data and methods to expose operations. So once a UA object has been defined in our server or has been imported via node set, it can be associated with a UCOS template, and we call that association a template binding. The template binding maps nodes of the UA object onto specific tags in the UCOS template. The user does this either via drag and drop or via an automated configuration, which we call a bind by name. So if you give your tag names the same name as variables or methods in the UA object, you'll get the benefit of automatic assignment to that object type. So UCOS command tags are a special type of tag that represents an instantaneous method call, and that's what gets mapped to methods. And all other tag types can be used to represent either method parameters or variables. So that would be, floats, analog ins, analog outs, digital ins, digital outs, text ins, and text outs. And once been applied to the UA object, then the device instances can be dragged into the global UA address space. So the strength here is that you express at the type level how a particular object is going to behave, and then with very little work you can create many, many, many instances of that particular type. So here's a few more specifics, which is that the solution for MDIS specifically provides a seamless layer over the existing FMC subsea control system using 722. Very little additional configuration is required to present this MDIS interface on top of the 722 system. We provide automated tools that generate the underlying UCOS configuration from the instrumentation configuration made by Smart Tool, which is our 722 configuration tool. And of course, our OPC UA platform independence will allow us to deploy this to numerous operating systems. So I'm going to demonstrate the server quite quickly. I'm going to go out to a virtual machine that we have out in the cloud, and I'm going to go through the process of configuring the basic parts of a server. So the first step is to simply associate the document with a UCOS project. And upon doing this, the UA server will scan the project for all the templates and device instances. And once that process is complete, you're able to see here in the window, we've got 4 templates, a choke, a valve, an analog instrument, and a digital instrument. Under each is the instances of all those templates. So these were created by connecting it to an actual subsea system and importing these. The next step will be to actually import the MDIS namespace, the MDIS object types and object definitions itself, the data model. So we'll import those. And once they have been successfully imported, we will go and create our template bindings. So I'll add a new template binding here. I can select my UCOS template. Let's just select the choke, for example. And we will also suggest, from the MDIS namespace, we will select the choke type. And once we've done that, what we see over here on the right-hand side of the pane are all the tags in the UCOS device. So this is a much larger set of tags than you may actually want to map onto the UA object itself. And what I'll do is I'll perform this bind by name. So wherever the name in the object type is the same as the tag name in the UCOS template, we will get a binding. So using this simple method, I've just now mapped an object in the control system out to an object in an object type. I'll do another one real quick. We'll take the valve, let's say, and bind it to the valve object. So once we've specified these bindings, the last step is to generate the namespace that the server itself will advertise. And we do this through what we call the server-defined namespace. And usually we group the objects into the well that they're contained on. So I'll create a folder for a particular well. And we'll call it well 1. And the final step is to place all the UA objects in there that apply to that well. So, you know, using some handy naming conventions and some selection filters, I should be able to select every device that we have currently defined on well 1. So we'll just select these, place those devices on well 1, and that's as easy as it would be to configure a live well. We've done this for an entire field on a server running on this machine, and that's what Vijay will use in his example to connect to. So at this point, I will turn the presentership over to Vijay.
Thank you, Andrew. Vijay, we're making you presenter.
You can hear me?
Yes, you're coming in loud.
Okay. Yep. Thank you, Andrew. And I'll give you a summary of Yokogawa's work in MDIS. Here we have looked at the MDIS architectures which Paul has shown you, and then we built our own architecture on top of it. And then we actually introduced a modular design concept for this, and then we have a UGS driver to connect to the UA servers. The UGS driver works on the universal gateway system, which acts as a gateway system for the MCS and the outside world. And then we are also addressing the graphics, and we have a driver which we are writing for the FCS, the actual controller. So this is a brief diagram of Yokogawa's implementation. We have two solutions. Both of them work for both integrated and interfaced architectures. So the differences between the solution is the nature of the solution, wherein the connectivity is done via the UGS or via the controller. So the reliability of the system which is actually required depends on which solution needs to be selected. Yeah. And a large part of our solution depends upon the node set files. If you see in the current day, the configuration is actually exchanged between the subsea server and the DCS via manually entered Excel files. Now this is actually prone to a lot of errors. So we are actually looking at making use of the node set files. So here, when the subsea systems, like subsea companies like FMC are generating their servers, they look at the information model, and then this information model is actually generated by the MDIS committee, and the MDIS committee is creating an MDIS standard information model, which is also delivered as an XML file, and then they would also use some OPC UA modeling tools to actually generate the model for OPC UA server. So now this model, the modeling tools can actually export out a node set file. If we do not have access to the node set file from a modeling tool, we can also export out the node set file from a running UA server. Now the beauty of this is the client and the server development, they can be totally be separated. So let us say like FMC is generating a server and Yokogawa is trying to connect to an FMC server, and both the client and the server are under development. Both of them can run parallelly, and FMC can actually give us a port accessible over the internet, and Yokogawa can connect to it and develop the client at the same time. So to consume this node set file, we have actually generated an import tool which would look at the node set file. The node set file contains all the objects which are present in the subsea system, and we look at the node set file and we generate a project which we can directly import it into our system, and the whole configuration is done. So what we have also is we have also created templates to map the MDIS standard objects. So each standard object would have a corresponding template in our system. So whenever we recognize an object in the subsea server and we say, okay, we use this template for that object, so we can directly have standard communication already happening. So here we just create some names, and then even if some server vendors or like let us say FMC wants to modify their object model. For example, MDIS actually provides a standard for how a valve should look like or how a choke should look like. However, FMC has come up with a new type of valve. Let us say they have added a new sensor onto the valve, so they have extended the model from the standard model. So what they would typically do is they would actually subtype the standard model and create their own model like an FMC valve. So from Yokogawa side, we actually modify the template to support the new extensions created by FMC, and then we can directly communicate with the extended objects. So the key feature for us is the modular design. So we are generating a subsea toolkit, and this is actually classified into 5 different layers based on the role it performs. So you have the IO layer, you have the device layer, and you have the unit layer, and the supervisory layer and the HMI layer. So the HMI and the supervisory layer actually performs the form the form the HMI or the interaction mechanisms to the objects. The unit and the device and the I/O represent the objects themselves. I'll show you a brief demo on how Yokogawa system would look like. So this is Yokogawa's DCS connecting to FMC's server. Now the beauty of it is like the FMC server is located in California, and we are here in Dallas. So this system would actually talk to an OPC UA, subsea OPC UA server, which is actually present in a remote location. So I can see if it works. I'm opening up a valve and then issuing a command, and yeah, the command works. So to make it more interesting, I'm issuing a close command. So if you see, I'm able to operate upon a valve from this. So now what the system is we have a standard objects, like we have the HMI layer for the valve, then we have one for choke, we have one for instrument. Now what this is once you have the configuration, once we extract the configuration in the form of a node set file, and then we import the we use our tool to actually generate the project and import the project. We have all the configuration done and ready for us. So all that is required from the client side is draw a graph which draw on a HMI which actually represents a subsea well, and then point out each item to a corresponding object in the server. So I can show you the tools which we use. Okay, this is the node set generation tool I'm talking about. So I'm just written a batch file. Now what this does is I'm connecting to the FMC Technologies server, and I'm trying to browse through their address space and then generate the node set files. I've run the node set file generation tool. Now this takes about 20 minutes because they have quite a big address space and we are over the internet, so it takes about 20-25 minutes. So probably will not be able to complete, I'll not be able to show you whether the generation of the node set file, completing the generation of the node set files. So then we have another internal tool which we call it as MDIS to UGS. Now what this tool does is, here just run this tool with a configuration. What this tool does is it will consume the node set files which are coming in, which we have the node set files, and then once the tool is run, you get a project like this. Now this project would actually contain all the objects which are generated. This is the controller, and you have the tags. So now these are all the objects which are present in the node set files. So these are automatically configured. Yeah. Yeah. So that is all what I have for now. Paul, you want to take over?
Yeah, thank you, Vijay. Thank you for the
Yeah.
nice presentation. What I will do is give you a quick summary, and then we'll open it up for some questions. So what we saw today was some information about the MDIS standard. We saw about the different architecture models that they support and that these are released already. We have a list of objects that we went through that both Vijay and Andrew showed how they've adapted their systems to dealing with these objects, and that the actual list of objects has already been released also. We have some validation work for MDIS that's still in progress, but we've had an IOP already where people brought products. At the next IOP, we plan on having actually released products and more vendors too. We have a recommended practice document that's in progress that provides sort of that additional information on how to deal with extensions and additions. So what we saw today was a very nice demonstration where Yokogawa was actually pulling data from an FMC system. The systems on both sides were configured with little or no work because of the object modeling. You know, it's just dragging and assigning things to templates and assignments. And the Yokogawa system can import a model very quickly. And this was extremely obvious at the IOP when vendors were able to switch between servers, the client vendors, the DCS systems, in a matter of minutes. So you could switch to talking to a different system. So in the old Modbus interface days, this would take, tremendous amounts of engineering and a great deal of testing. And now it can happen very quickly, very easily. So we have a set of specs. The formal release of the MDIS specification is targeted for after the next IOP. Why so late? Well, we want to make sure that the OPC Foundation's learned its lesson. You don't release a standard until you actually have running versions of things. So at the next IOP, people will be bringing running versions. So we'll release the standard following that. So with that, I think, Vijay, if you move to the next slide, we're opening it up for some questions. And by the way, if you're interested in more information about MDIS, the URL at the top of the screen will give you additional information about MDIS. It's the link for the MDIS systems. So let's see what questions we have. I have a question here about, so the demonstration was just from FMC and Yokogawa. You listed some DCS vendors, but what other subsea vendors are involved? I guess I can answer some of that, which is that the list of subsea vendors that were at the last IOP included companies like Cameron, OneSubsea, ProServe, Acre, GE, and then there's others too that are working on it. So the subsea system actually has quite a few. If you want the full list of who's involved with MDIS, you can go to that URL for the MDIS network, and they publish a list of all the currently active companies, including the operating companies that are working on it. I have another question here on, have there been any projects using MDIS or OPC UA? So maybe I'll see if, I'm a consultant that deals mostly with OPC UA. I know there's OPC UA been used in industry a lot, but maybe I'll let one of the other, either Andrew or Vijay, talk about projects using MDIS. So do you guys have any comments?
Yeah, Paul, this is Andrew. Most of the operators are very excited to use it, but they're waiting for the first official release of the data model. So I think for use of MDIS itself, that's where they're going to wait probably until later. next year. I don't know of any specific job that's using MDIS itself, but as you've said, OPC UA is used in many different disciplines of control systems, and that much I am sure of.
Okay, thank you, Andrew. So there was another question here about what is the advantages of OPC UA over Modbus? So I don't know, maybe I'll let one of you guys provide that information too if you would like, or I can also have a little bit to say too. Vijay, do you have anything to say there, or Andrew?
Yes, yeah, this is Vijay. Actually, Modbus, all the communication happens in bits and bytes. So what happens is configuring a system which works on Modbus is quite cumbersome. Versus OPC UA, you can actually standardize the objects. The OPC UA forms the object model. So you can standardize the objects at the server side and the client side. So once you have standardized, connecting both the client side objects and the server side objects is quite simple.
Okay, that's thank you for that answer. Andrew, do you have anything else you want to add, or are we good?
Yeah, I would also add to that two key features. One is the ability to browse. In other words, that it allows the server to advertise all the data that it's exporting. And the other is the ability to grab a snapshot of a node set from that browsing capability. So that it allows you to define what the interface is going to be very early on in the project. And subsequent changes to the data model don't invalidate anything that was there before. So you can really establish the bulk of what the address space is going to look like prior to the integration phase via the very simple steps. And I think that's something that's very powerful that no other protocol has really delivered before.
Thank you, Andrew. A little addition that I also, from my experiences with Modbus, is that Modbus doesn't have security. It doesn't have some of the robust communication capabilities that OPCA would provide too. So the error handling and the security aspects of UA add a great additional feature that you won't get out of Modbus. So there's quite a bit of difference between the two. Let's see what else I have for a question here. This is one I think I'm going to end up having to answer, which is OPC UA released and is it available? So yes, OPC UA has been released for many years. It's made some fairly strong inroads, as Andrew has said, into a number of interfaces and architectures. So it's used in building automation. It's used in industry, in particular in Europe. The German train system uses OPC UA. It's used in a number of fields, and it's expanding very rapidly at this point in time. And there are a number of other companion specs, not just the subsea MDIS spec, but there's standards for ISA 95 and OPC UA. There's ones that are being worked on for surface drilling. There's PLC open, so PLC to PLC communication standards. So there's a great deal of OPC UA activities and work going on. Industry 4.0 in Europe has chosen to use OPC UA. So yeah, so OPC UA is released and it's actually fairly widely adopted at this point already. So I see one more question, which maybe the question will sort of end on, which is, will this webinar be available as a recording? So yes, we are recording this webinar. We will publish it and send it out to all the attendees and even the people that missed that did register though. The foundation may actually even post it someplace online for people to access it. Unless I get any more questions, I think that will be it. This is Paul. Thank you very much for attending. Andrew, Vijay, thank you for presenting and providing us a nice insight into your individual systems.
Thanks for having us, Paul.
Thank
Thank
you.
you, Paul.
Bye, everybody.